degree freedom, 1 degree freedom vibrations. This is the response will look like, and the response usually is being written by the sinusoidal oscillation, for example, cosine omega dt minus phi. And this is oscillation, and its magnitude is in exponential decaying. So that would be in certain magnitude multiplied with exponential minus zeta omega nt. So that is the general form of such oscillations. And in particular, when we are dealing with mx double dot plus cx dot plus kx equal to 0, and or if you convert it into a standard template, okay, so for either case, the characteristic root is P is minus zeta omega n plus minus j omega n 1 minus zeta squared. Okay. So that is the preparation for this one, and then the features is this: the exponentially decaying at a rate. That rate actually equal to the real part of the characteristic root. And someone steal my red pen. Okay, let me check this one. And the oscillation in the frequency, and that frequency is governed by the imaginary part. So this one we define is omega d, if you remember our definitions. Okay. So that is kind of easy. From this kind of the mapping, we can kind of easily write up the form like this. Okay. So given any, once you identify the underdamped vibration systems, you don't need to start over from the beginning to solve that equation. You can right away to jump into this form. Okay. And in this form, the capital X and phi, the two unknown variables, we can solve by two initial conditions. Equivalent descriptions of this form can also be written by this. If you you can also be written by the oscillation cosine and with the phase angle. These terms together with x, you can decompose into combination sine plus cosine. Okay, so equivalent form you can be like the C1 cosine omega dt plus C2 sine omega dt. Okay, so basically x and with cosine, this term can be expanded by this. And this one is in combination of cosine and sine with certain magnitude. And again, this is a pure oscillation of the sinusoidal functions. And the magnitude actually will be decaying. Again, we keep this one here. Okay? So either way, depends on which form and depends on the information. Either way will be okay. And sometimes start with the second form will be easier. Sometimes starting from the first one will be easier. Depends. Okay. But if you pick either way, and actually that will give you the same result. So last time we have seen one example here. We've seen this example. Let me rewrite this one again. 5x double dot plus 2x dot plus 50x equal to 0. And we solve for characteristic root for these equations. For this problem is equal to minus 0.2 plus minus j and 3.156. Okay. So again, from here we can plug into this template and we can exercise again. And let me exercise the first form, and that is the magnitude with exponential decaying. The decaying with a rate. That rate is governed by the real part, minus 0.2. Okay, and time cosine. And that is sinusoidal oscillations. The oscillation is in the frequency omega d, and that is the imaginary part, 3.156t. And right now we are currently in the combined form, so here we consider a phase angle here. Okay, x and phi can be solved by initial conditions. And our initial conditions, last time we are given x0 equal to 0.2 and x dot 0 equal to 2. Okay, so we have two initial conditions we can solve for this one. Or otherwise, you can express into this minus 0.2t, and again, we can expand x multiply with this one into c1 times cosine 3.156t and plus c2 sine 3.156t. Okay, so either way, and so last time we solved, and not to repeat the whole calculations, and the C1 we solved is minus 0.2t, and C1 last time we solved is 0.2. Okay, so let me rewrite here, 3.156t, and plus C2. C2 equal to 0.6164, and sine 1/60. Okay, so that is what we done last time. So now the question is, say, if we want to solve for what is x, so based upon the information, what is x? If you remember that the x is, we learned before, is c1 squared plus c2 squared. Okay, we've seen this one before. Okay. So from here we can get the x1. Then I leave this number for you to calculate. Okay, I don't have the exact calculations. And phi, we can do this one again. I remember this formula. I forgot this formula. I don't have that formula written on my sheet. So here we,
Is it arc to the end, like C1?
The arctangent of something, right? Yeah, so this is the arctangent of something. And something that is either C1 divided by C2 or C2 divided by C1 or whatever. And under these situations, let me show you my kind of thinking process. So under these situations, I simply expanded this one, x cosine 3, let me omega dt. Okay, omega d equal to 3.156 minus 3. I simply expanded this one. So cosine, we expanded equal to cosine omega dt cosine phi. I'm going to use this equation cosine a minus b equal to cosine a cosine b plus sine a sine b. I'm using these equations here. So plus sine omega dt and sine b. Okay, and then I distribute x into individual terms, and then I collect. So that means omega cosine omega dt with its coefficient capital X times cosine phi. Okay, and then sine dt, omega dt, with the coefficients is capital X multiplied with sine phi. Okay. So under these situations, you can see from here, this is our C1, right? And this is our C2. So we have such relations here. C1 equal to capital X cosine phi, and C2 equal to capital X sine phi. So from here, you can see we take the square, C1 square plus C2 square, equal to this term squared plus this term squared, that is capital X squared. So that reason I know that is the equation there. Okay. So from here we have this one, and then we divide each term side by side. So that means C1 divided by C2 equal to this term divided by that term, x cosine v, x sine v. And so from here we can cancel x, and or otherwise C2 divided by C1, then we reverse, equal to sine v cosine v. Okay, and this one basically equal to tangent. So therefore from here I know the tangent equal to arctangent, the v equal to arctangent C2 divided by C1. Okay. So once you have these numbers, you simply plug in, and be careful. Some of calculators, they allow you to kind of a setting, either you operate into degree or radians. Okay, so get that setting correctly, and sometimes we like to express it in radian. Okay, so in this kind of form, all the units in there is radian. For example, say omega d is in radian per second, then this v you better to use the same radian, right? Okay. So that is the information we exercise here, and in this exercise, yeah, I kind of show you kind of reversions of between the two forms. So basically, you can either determine C1, C2 from initial conditions, then get x1 and v from that formula, or vice versa. Good? Okay. Then we can do a little bit more exercise. Before doing exercise, and let me do this one here. So right now we have the calculation. So let me plot this form here. So okay, so the oscillation will be something like this, and again, this exponential is capital X times e minus 0.2t. Okay, and this is the first, the amplitude. Let me call it x1. How about this? Let me just change the symbols. So this is the amplitude, and let me call it A1. This is the amplitude here, and let me call it A2 here. Okay. And right now I'm going to do is this. Sometimes people are kind of interested in how fast the vibration is going to suppress. So that means how fast the amplitude is going to decay. So that is another more quantitative quantification of this approach. So the people like to do this. They like to compare A1 divided by A2. They want to see the ratio. This is a decaying in one period. So if we know this one, then basically follow up, the decaying per period will be repeating by this ratio, right? Okay, so we're starting from here, we see how can we calculate this one. So this one, right now, let me utilize this form, and let me pick up this form, that'll be easier for us. So A1 is the magnitude. For example, let me designate, say it's happened at the time T1. And of course, we can determine T1, right? And how do we know, how can we determine T1? T1 is derivative, right? I heard about that kind of keyword. So d over t, we take the derivative of the displacement. When that information equal to 0, corresponding would be either this point here or this point here, right? Either way. So we take this equal to 0, and from here, we know we will have T star equal to multiple solution T1, T2, etc. T1 corresponding to here, T2 corresponding to here, T3, T4, etc. And we pick the smallest one. The smallest value that will give us the T1, that will give us the moment when the first peak will appear. You okay? Okay. Anyhow, like just saying, we are able to calculate T1. Okay. And now this one happened at the T2. And actually T2 is a 1 period after T1. So really we can try is see T2 equal to T1 plus the period. 1 period. And what is period? Period equal to 2 pi divided by omega d, right? Omega d for this particular case is 3.156. Let me use this one, omega d. Okay? Okay, so now we can plug in here. So what is A1? A1 is the magnitude of x at T1. And A2 is the magnitude of the displacement at T2. T2 is T1 plus omega 2 pi divided by omega d, right? We simply plug in the information here. Then we can do the detailed calculations. So that means for the numerators, we plug in T1 equal to here. So that is capital X multiplied with E minus 0.2T. And here we plug in T equal to T1. And times cosine and 3.156T. And now T is plugged by T1. And minus phi. Phi is a certain number, we just leave it. Okay. And now the actual, and then again is E minus 0.2 times. Now the for A2, then we plug in T equal to T2, and that is T1 plus 2 pi divided by omega d, right? And yeah, I kind of omega d here kind of swap with these numbers, 3.156. Okay, now cosine 3.156 and T2, that is T1 plus 2 pi divided by omega d. Omega d equal to again 3.156. Okay, we'll leave it there. And now from here we can do the cancellations of some common terms here. So before doing that one, why not let me do a little bit more. So these terms, and we can expand it. Basically this term is exponent minus 0.2t multiply with exponents minus 0.2t. And so let me going back. 0.2 is our zeta omega n. Okay. So let me do some kind of the symbolic with a numeric kind of replaceable things to show you some physical things inside, and multiply with 2 pi. What is omega d? Omega d is omega n times 1 minus zeta squared. Hopefully you know what I'm saying here. Will be okay? Okay.
Question.
Yes.
Is the t part of that zeta omega n? Is that t part of that supposed to be there?
Where?
Right there. Yeah, where you're pointing.
Yes.
It is.
Omega. T1. So this is T1.
Okay.
Yeah.
Okay.
Because right now I expanded, I distribute 0.2 equal to zeta omega n. Right?
There's no T.
T1.
The T1 should only be in the first exponential.
Yeah. So
Okay.
at that point. Sorry.
Cool.
Thank you.
It's all good.
Okay, so with these things, and we have a numerator, we have a denominator, we begin to cancel the common terms here. And this is a common term. Okay. And then how about this? Cosine this term, can you see basically this term is equal to cosine of this one equal to this one? Do you know why? Because this is a cosine at T1, this is a cosine at the value of the cosine at one period after at the same. So basically the two numbers can be cancelled. Okay, so leading to here. So that means leaving this one, we have only one term, denominator and numerator equal to 1. Denominator leaving this term here, let me write into here. And denominator only have this term, let me rewrite that one, minus omega n times 2 pi omega n 1 minus theta squared. Okay, so from here we can have more derivations. We cancel omega n here. Okay, we almost done. So that means this one we have is 1 exponent minus theta minus 2 pi theta divided by this one. Okay, and this one actually equal to exponent. We do one more term, flip. Okay, so under these situations, people say, why not we take the log? So if we take the natural log to here, so therefore, let me move up to here. So the natural log of A1, A2 simply is equal to 2 pi times theta, like this one. Okay, so we compare the ratio. The ratio tells us how fast the decay is. And the ratio, you can see, is only governed by the damping coefficient. Okay. So damping coefficient is the only thing, is the only parameter that will govern how fast this decay will be. And also that is showing here, omega minus 42 there. Okay. So keep this in mind, and later in at one side we will specifically dedicated to this discussion one more time. So, but anyhow, this is kind of the exercise. So for our example, you can plug in the number here to see what happened there. Okay. So here we have more quantitative tool, and we can analyze the vibration, how fast the damped system is. And so this section will stop here.